C'est le temps de commencer. Je suis Robert Boyd, and I will be the master of ceremonies for the first half of the symposium, and Paul Corcoran will take over for the second half of the symposium. Let me just remind you that this is the fourth Schawlow-Townes Symposium, and behind me is the announcement for the very first Schawlow-Townes Symposium 4 years ago. And you'll see that among other illustrious speakers, one of them was Charles Townes himself. So he was here to inaugurate this event. So why is there such an event? Well, shortly after my coming to Ottawa, Paul Corcoran and I had a discussion of what we could do to celebrate the field of photonics. The University of Ottawa has made an enormous commitment to the field of photonics. And, well, Paul and me being here is part of their commitment to the field of photonics. And we wanted to just have a celebration, like a birthday party for photonics as a discipline. We decided as a name Schawlow-Townes. Art Schawlow, of course, is Canadian. Charles Townes was his brother-in-law. So as his student, I always was told very, very good things about Canadian physics. So it just felt naturally for me to come here. Okay, so that's the happy part of this presentation. As I think you all know, Professor Townes passed away earlier this year. He was 99 years old, would have turned 100 on August 22nd? No, I guess it's July 28th. I should read my own slides. Okay, so Charles Townes passed away earlier this year. A great loss to the community. He, of course, was the inventor of the maser and the laser, won the Nobel Prize 1964, advisor to 3 US presidents, and was my teacher, mentor, and friend. In the light of today's presentation, I think today's event, I think a strong argument can be made that he was the father of the field of photonics. Of course, we wouldn't have photonics without the laser. He also discovered fundamental nonlinear optical processes, including the Outward-Townes effect, self-trapping of light, which is now called optical solitons, stimulated Brillouin scattering. Townes was a very humble man. He did not put his name on the papers of all the papers that came out of his research group, but light-by-light scattering is sort of the essence of photonics. It's the fact that one beam of light can control another beam of light, and that was probably the part of his legacy that is most directly related to what we mean by photonics today. And I'll just end with this, because it's a great portrait of Professor Townes, and maybe not everyone knows that Joseph Karsh, who became famous by his portrait of Sir Winston Churchill, also took a portrait of Professor Townes. So with those as my brief introductory remarks, I would now like to call our Associate Vice President for Research, Sylvain Charbonneau, to give the official welcome for you to be at our university.
How am I supposed to match those comments, Bob? So, bonjour tout le monde. Il me fait plaisir de vous souhaiter la bienvenue ici sur le campus de l'Université d'Ottawa. Mon nom est Sylvain Charbonneau et je suis vice-recteur associé ici à l'université. Il me fait plaisir de vous souhaiter la bienvenue à ce 4e symposium Schawlow-Townes. So I'm very pleased to welcome you to this 4th Schawlow-Townes Symposium in this International Year of Light-based technologies. In proclaiming the International Year focusing on topics of light science and its application, the United Nations has recognized the importance of raising global awareness about how light-based technologies promote sustainable development and provide solutions to global challenges in energy, education, agriculture, and health. Light plays a vital role in our daily lives and is imperative cross-cutting disciplines of science in the 21st century. Recognizing the importance of international collaboration in photonics research, On May 26th of this year, the University of Ottawa officially entered into a very strategic partnership with the Max Planck Institute for the Science of Light and Air Langid, and became a designated Max Planck Center for Extreme and Quantum Photonics. One of only 3 in the Americas, I should add. This official designation will allow researchers from both organizations to develop synergies and facilitate exchanges between the 2 countries. This forward-looking partnership would not have been materialized without the leadership of Professor Gerd Leutsch, director of the Max Planck Center, who is here with us today, as well as our own Robert Boyd, the Canada Excellence Research Chair in Quantum Nonlinear Optics. Thank you, Gerd. Thank you, Bob. It goes without saying that photonics is an important strategic area of development of research for the University of Ottawa. Less than a year ago, the university inaugurated the opening of its advanced research complex, a $90 million state-of-the-art facility dedicated entirely to research in earth sciences, advanced materials, and photonics. This important investment was only the beginning. Earlier this year, the university was successful in attracting $32 million in research funding from the Canadian Foundation for Innovation to further its research in the field of coherent X-ray photonics, a technology unifying materials, imaging, and ultrafast science, as well as in advanced materials for designer molecules and transformating devices. Thank you to all the principal investigators who put a tremendous amount of effort in putting these successful applications, many of whom are in this room today. Focusing now on this symposium, for the first time this year, the organizers have integrated an industrial component to the program. The session which is to take place right after lunch will provide an opportunity for a few local photonics employers to highlight their organizations. I would like to conclude by congratulating the organizers for putting together an outstanding program for this year's event. Our 2 co-chairs, are we co-chairs? Bob and Paul? Paul, we're co-chairs? Yeah, okay. Thank you very much for putting this tremendous program together. And there's a lot of people behind the scene, and I know I'm going to forget some. If you can just put your hands up. So Hugo Bégin in the back, Judith Lachance, Ben Sussman, and there's probably many others, so I apologize for forgetting some. And finally, I would like to acknowledge the long-lasting strategic partnership with the National Research Council. Merci beaucoup, and I wish you a very great symposium.
So, Sylvain, thank you for those very kind remarks. One never disagrees publicly with a vice president, but Paul and I realize there are 3 co-organizers. Ben Sussman from National Research Council is the 3rd co-organizer of this event. So I want to thank Ben as well. Is Ben here? Ben is here, yeah. He flew in last night from Japan, was it? Yeah, so you were here. Okay, so next I would like to introduce Duncan Stewart from the National Research Council, which is the co-sponsor of this event. And Duncan is going to make a few remarks about this event to help welcome you here.
Thank you, Bob, for the introduction. Bonjour à tout le monde. Merci, Paul et Bob, for creating this excellent symposium. Thank you, Ben, as well. Thank you to our distinguished speakers, Professors Serge Haroche, Nader Angeta, Ferenc Krauss, and Moti Segev. We're honored by your visits. Canada, for me, is actually at a crossroads in how it approaches science and technology research and development. We all recognize that in most cases, market forces prohibit medium and long-term investment in R&D from the private sector. We also all recognize that sustainability of any developed society requires exactly that investment in medium and long-range R&D. It's actually too risky not to do it. To achieve impact, that research also needs to be developed and deployed. But the question is, what do we do and how do we do it? In Silicon Valley, the most common question that graduating students, masters, PhDs, including physicists, asked each other was, am I going to work for you or are you going to work for me? Even physicists. I lived that. Two of those Stanford students were Bill Hewlett and Dave Packard. Their startup is today a $100 billion business employing 300,000 people. They had a simple three-step recipe for evaluating new ideas. Listen, encourage. Then, after a short time, come back with some tough questions. Specifically, is the work behind this really excellent? And is it relevant to the company? Then, after another short time, they would come back and they would issue their leadership decision. It turns out that Bill Hewlett had an increased bent for physics and engineering, and Dave Packard had a talent for business. So their questions and the decision always included those two factors. It's almost an equation. Excellence times relevance equals impact. If both excellence and relevance are high, the impact is likely to be high. If only one variable is low, the impact is likely to be low. Excellence is often easy for us to judge as scientists and engineers. We know where we stand with respect to our peers. Relevance is harder to assess, and sometimes it even seems quite fickle. Certainly, the flavor of the year in science and politics is fickle. But the long-term goal of high-value jobs in Canada is not fickle. I would posit that every student in this room wants one of those high-value jobs. Nortel Networks previously owned more than 80% of many telecom market segments. That story didn't continue the way we hoped, but it does indicate the extraordinary strength of photonics and industrial photonics capability in Canada and in Ottawa. And it indicates to me that if we lead excellent R&D in the next generation of photonics, we can also lead relevant development and deployment of that research. The National Research Council, which I am honored to represent, is very proud, Sylvain, of our collaboration with the University of Ottawa in the field of photonics. We've both committed enormous resources to this over the years. At NRC, Dr. Ben Sussman leads our 40-person, $7 million a year effort in quantum photonics sensing and security, based on the excellence of the labs of Paul Corkum, Dave Villeneuve, Albert Stolo, Stefan Mihailoff, Ben Sussman. University of Ottawa has built a new lab from the ground up in the last few years, gathered their best photonics faculty from physics and engineering, and recruited you, Professor Boyd. It has built a partnership with the outstanding Max Planck, Professor Lux. And that is actually what is required to win. I can't wait until University of Ottawa students are asking themselves, am I going to work for you, or are you going to work for me?
So now it's my great honor and pleasure to introduce the first technical speaker of today. It is Professor Serge Haroche from the Collège de France and from the École Normale Supérieure in Paris. Dr. Haroche was born in Casablanca, Morocco. He moved to Paris as a child, received his undergraduate education at École Normale Supérieure. He did his PhD work under the supervision of Claude Cohn-Tanuji, and dressed state analysis played a key part of his PhD thesis. His thesis was technically given by Paris SACE, because ENS, as I understand, does not award PhD degrees. After this, and not irrelevantly to why we're here today, he became a postdoc in the group of Art Schawlow at Stanford University. Later in his career, he worked on many topics, superradiance being one, and especially cavity quantum electrodynamics, cavity QED as we call it. And his work in this area led to his being awarded the Nobel Prize in Physics in the year 2012. So please help me welcome Professor Haroche to our symposium.
Thank you very much, Bob, and thank you, Paul, for inviting me to this symposium. I'm very happy to have an opportunity to pay tribute to Townes and to Art Schawlow. As you mentioned, I was a postdoc with Art back in the 1970s. It was my first work outside the lab in which I got my PhD, and I have very fond memory of this time. It was a very exciting time for laser physics, the beginning of laser spectroscopy, a field to which Art Schawlow has contributed a lot. And it was also a good time in my personal life. Art was a wonderful man, not only a scientist, but also a human being. He was full of humor and gave me a lot of good advice, not only during that time, but later on, because myself and my wife, we were very good friends of Art Schawlow, and Aurelia Schawlow was the sister of Schawlow-Townes. I think it's a good opportunity to talk about lasers, of course, because lasers have played a very important role in physics, and during the last 50 years, they have allowed us to make wonderful physics and wonderful experiments in all kinds of fields in physics and chemistry, and I would like to put this in perspective. I think it's also a good opportunity to talk about light in general. As we have seen, this year is the International Year of Light, and I would like to recall first why we celebrate light this year. It turns out that this is, by coincidence, the anniversary of many discoveries which have been essential to understand light and its mysteries. 1,000 years ago, the Arab scholar Al-Hazen has written the first theory of optics, in which he described light rays and made clear that light was not coming from the eye to the object, but from the object to the eye. 200 years ago, Augustin Fresnel, after Thomas Young, claimed that light was a wave and a transverse wave, which was oscillating perpendicularly to its propagation. And we had to wait 50 more years, of course, to understand the nature of this wave. Light was an electric and magnetic field propagating in space at the velocity of light, of course, and this is Maxwell's equations. And then reflecting on Maxwell's equations and on what they mean really and what means the velocity of light, Einstein developed the special and then general theory of relativity, and we are celebrating the 100th anniversary, 1915, which was the birth date of Charlie Townes too. And then 50 years later, Penzias and Wilson discovered serendipitously the black body radiation background by trying to clean a radar antenna, which gave a lot of noise, and they didn't understand this noise, and it turned out that it was a black body background, which plays such an important role to understand the origin of the universe and gave a great impulse to cosmology. And back in 1965, Charles Kao, a Chinese engineer working in England, developed the ultra-transparent fibers, which, coupled to lasers, were the origin of the network of the optical networks that we use for the internet, for instance. So these are very interesting years, and it turns out that 1965 is also very important for me because it was the year I started my own career in physics. And I had the luck to work in the lab of Kastler and Brossel. This is a picture which was taken in 1966 on the day Kastler got the Nobel Prize in Physics for optical pumping. He developed methods to use light in order to manipulate atoms, to put atoms in states which are not in thermal equilibrium. This was called optical pumping. It was using not lasers at that time, we were using spectral lamps, classical light, but then, of course, optical pumping was extended with lasers. And on this picture, you can see Claude Cohen-Tanuji, who was my thesis advisor and who was a student of Alfred Kastler. And on the right, you can see Jean Brossel, who was a colleague of Kastler and was really the man who did the experiments about optical pumping. And I was amazed to be in such an environment and to find myself in a place where such good physics was being made. Of course, lasers were already around, and we knew that lasers were announcing exciting time for physics, but we could not imagine the magnitude of the progresses this new tool would bring. In fact, one can say without exaggerating that we have won about 10 orders of magnitude in many domains And when 10 orders of magnitude is, of course, a quantitative statement, but when we get into these numbers, it becomes qualitative, and a lot of things which could not imagine could have been done since. Of course, one of the great scientists that we have to remember is Einstein, not only for relativity, but also because he had the idea of stimulated emission. It was the beginning of quantum physics, and the first theory of the atom have found that atoms, when they are excited, come back to their ground state by a quantum jump and emit a photon. This is spontaneous emission. But by studying the interaction with light with matter and trying to understand the equilibrium of light and matter, what is called the black body radiation, Einstein came to the idea that on top of spontaneous emission, when the atom was excited and when he was interacting with photons which had the right frequency, there was another process which he called stimulated emission, which made the atom emit preferentially in the mode of the light which was coming in. So one photon triggers the emission of a second photon and so on. And this is the amplification of light, which is, of course, a process used in the laser. So the recipe to build a laser is to have a lot of atoms that you excite by a process, which can be light or an electric discharge, for instance. And so the first photons are emitted spontaneously, and then the light is amplified when it's going back and forth, for instance, between mirrors. You have to build up a cavity. And if one of the mirrors is slightly transparent, you get a light beam getting out, and this is a laser beam. This is very easy to say now that we know how it works, but of course, it took 40 years from Einstein to Townes, and the first lasers were not working, as you know, in the optical domain, but in the microwave domains. They were called masers. And this is a picture which shows Townes and his student Gordon, who built the first microwave amplifier. It was, the medium was ammonia molecules, and it was an atomic beam that you can see on the picture. The population of the excited state was achieved by the simple Stern-Gerlach method, which prepares the atom in one spin state, in one magnetic state, and then these molecules went into a cavity which was resonant with microwave transition, and the system started to oscillate. I want to say that this comes from the work which was performed at Columbia in Rabi's group. Townes came to work at Columbia, and Columbia was well known for the molecular beam method, which was a method that Townes used. And Rabi was, of course, the grandfather of all these technologies, not only of the laser, but also of the atomic clock and of NMR. And these methods were also helped a lot by the technological development during the war, the technology of the radar and the microwave technology. I have attended a lecture by Gordon a few years ago in which he said that while he was trying to build the maser, Rabi used to come in the lab and explain him why it would not work. And the same happened with Niels Bohr. Niels Bohr visited his lab about 10 years before he died and tried to explain why theoretically the maser and the laser would not work. So you have, this is an advice to young students, you have not to listen too much to what famous people say because they can make mistakes. So once the maser worked, of course, the next step was to try to do it in the optical domain, and here comes Arthur Schawlow, who worked with Charles Townes, and they wrote a famous paper in 1958 called The Optical Maser, in which they explained how you can pump atoms and what kind of cavity you need. And it was the beginning with Fabry-Perot cavities. In fact, Townes had come to Paris to work with Kastler before I was a student there back in the 50s, because he saw that one method to achieve the population inversion would be to use optical pumping. In fact, it's not the way it worked, and the first, as you know, the first laser was developed by Theodore Meyman. It was a ruby, a solid-state laser pumped by a flashlight. It was a pulse laser, and then a few months later, the first CW laser, gas laser, was built by Ali Javan. It was a helium neon laser emitting continuously in the red. So this is his story, but since then, as you know, the laser has been developed into all kinds of forms. It's a fantastic tool, and I call it tamed light because as opposed to ordinary light in which atoms emit independently from each other, light which has a lot of stochasticity in it, there all the atoms emit in the same beam, and it's a light beam which has absolutely extraordinary properties. And now it sounds familiar that you can have lasers like this laser pointer, for instance, but back in the 50s, it was really a miracle to have a light beam like that. And the properties are really contradictory. The light beam can at the same time heat matter at extraordinarily high temperature. You can, if you focus an intense laser beam on a piece of matter, you can heat it to millions of degrees and produce situations which occur inside stars and initiate nuclear reactions. But at the same time, you can use intense laser beams to cool matter at extraordinarily low temperature, reach the coldest objects in the universe, realize BoseEinstein condensation, for instance. In another domain, lasers can be ultra-stable. You can have light beams which oscillate without skipping a beat over millions of kilometers, which means that you can use interferometric method to measure distances within 1 micron over huge distances. And in the time domain, you can count this oscillation of light and realize atomic clocks which keep time with a precision of a few seconds in the age of the universe. So very steady and continuous wave, but you can also concentrate light into bullets of light which are a few tenths of angstrom long and which last a few tenths of attoseconds. So this is absolutely extraordinary, and this leads to a lot of experiments to study the properties, fast phenomena in atoms, molecules, and solids. And here I'm talking only about basic research, blue sky research. Of course, laser has been very useful in a lot of applications in medicine, in communication, and so on, but I don't have time to talk about that. I will concentrate on research. And what I want to say is that you can, in fact, divide the history of the laser into decades. The first decade was the 1960s. It was the birth of the laser and using it to perform optical pumping. At that time, laser had fixed frequencies, and it was very difficult to use them in precise spectroscopy experiment. Then came the tunable lasers, and a lot of high-resolution laser spectroscopy methods were developed in which you can beat the Doppler effect and find the natural width of the atomic or molecular levels. This happened in particular in the lab of Art Schawlow and Ted Hench in Stanford, and I had the luck to be there when this development occurred in the 70s. Then in the 1980s, the laser cooling of atoms came, and also the beginning of cavity QED, which studies the properties of atoms and photons inside cavities protected from the outside environment. And it was also the beginning of ion trap physics, and I will say more about that later. Then in the 1990s, quantum information developed, the fact that you can use the manipulation of single atoms or single ion to store information, not in a classical way, but in a quantum way using state superposition and entanglement. It was also the beginning of the Bose-Einstein condensation and also the development of ultra-fast laser technology. Then the year 2000, all this became even more sophisticated, and atomic physics made connections with condensed matter physics. Instead of using real atom, artificial atoms like Josephson junctions in circuits could be used to manipulate quantum superposition. Attosecond physics, of course, developed in this decade. And I think it was a very interesting time, and we are in a very interesting time because atomic physics is meeting a lot of other fields, as I will say a little bit later. Now, to come back to my initial statement that about orders of magnitude, I will give you a few examples here. In terms of precision of spectroscopy experiment, in the 1960s, making a measurement with 8-digit, 10⁻⁸, was considered already very good. And this corresponds to a clock which would be stable within 1 second in a year. Now we are talking about spectroscopic methods which allows us to achieve a precision of 10⁻18, that is 1 second in the age of the universe. So it's 10 orders of magnitude. Sensitivity of measurements. In the 1960s, if you had a cell containing a low-pressure gas, you were working with 10 to the 10 atoms at a time, and it was already considered as a very dilute medium. Now we are working with single atoms or single photons, again, 10 orders of magnitude. Temperatures. Temperatures were between 1 room temperature is 300 K. If you cool down to 1 K using liquid helium, it was considered as being very cold. Now we are talking about 10 minus 10 Kelvin temperatures in the pico Kelvin range. So it's again this huge order of magnitude. And now about speed and time resolution. Flashlights, if you achieved 1 nanosecond, it was considered as a tour de force. Now, you know that you can reach the attosecond level. And I could go on and on. I could talk about the intensity. If you concentrate the solar light on a few square centimeters, as in a sun furnace, you get kilowatts per square centimeter. Now we are talking about 10 to the 20 or 10 to the 22 watt per square centimeter. So now it's not 10 orders of magnitude, but 15 or 16 orders of magnitude. So let's say a few words about temperature. This is a log scale where you can see the temperature inside the stars, sun surface, a few thousand K, room temperature, the cosmological background, which is around 3 Kelvin, and all the technologies of liquid helium, which bring you maybe down to a few millikelvin. With lasers, you reach, in the mid-80s, Doppler laser cooling, which was a few 200 microkelvin, and then by sub-Doppler cooling techniques, the microkelvin range. And then from the microkelvin, using evaporative cooling, I would say a few words about that, you get into the range of the nanokelvin. And if you take a look about the velocities of atoms, at room temperature in this room, the atoms are going at 500 meters per second, Doppler cooling bringing it down to meter per second, and evaporative cooling to millimeter per second. As you know, the de Broglie wavelength is inversely proportional to the velocity, and so it means that you get into the range where atoms have a matter wave which extends over macroscopic distances, and this has very important consequences, and this leads to these new phases of matter. So how do you cool atoms? I don't have time to enter into details, but you realize counterpropagating beams of laser light, and the trick is to detune the laser slightly below the resonance, which means that due to the Doppler effect, the atoms will always interact more with the light which is coming towards them than the light which is in their back, and this gives rise to a force proportional to the velocity, a damping force. This is why we call the system optical molasses. The atoms are like small pieces of matter inside a molasses, and they come to rest at a very low temperature. Once you get to this temperature, you can switch off the light and realize a magnetic trap. You realize gradients of magnetic fields which are strong enough to keep the atoms at the bottom of the trap because they are already cold. And now these magnetic traps are working only if the atom is in the right magnetic sublevel. If it goes into the wrong sublevel, the force becomes anti-trapping. And this gives a very astute method to cool down even more. You apply a radio frequency field which is resonant only if the atom comes to the edge of the trap. Then they flip to the other state and they escape. This is called evaporative cooling. The fastest atoms escape, and the rest re-thermalize by collisions. Of course, you have to do it in the right way because you must cool before losing all the atoms, and this is why it took some time to realize. When you get to very low temperatures, because of the de Broglie wavelengths, as I explained, the wavelength increases, and if the atoms are bosons, and when the distance between them becomes of the order of the de Broglie wavelength, they condensate into the ground state of the trap. This is called BoseEinstein condensation, which was predicted by Einstein in 1925 and observed for the first time with his cold atom in 1995. This is the technique is simple. The principle is simple to explain. Once the system has got into this state, you switch off the trap, so the atoms will escape, and after a while, you take a picture by taking the shadow of this expanding cloud. And this gives you a distribution of the velocities of the atoms when the trap was switched off. And you will see the picture which comes from the group of Cornell and Wyman, who were the pioneers, who were the first to observe that. You see in this movie what happens when the temperature goes down, and suddenly when you reach the threshold, you have a peak of atoms which which are in the ground state. You just have the 0-point fluctuations of the trap. And you see you have two temperature scales, because as you go down in temperature, you lose atoms. And if you lose atoms, the temperature for the threshold increases because the double wavelength becomes bigger and bigger. And so you reach the threshold if you are clever enough to have the temperature decreasing faster than the threshold of the BoseEinstein condensation. And this made, of course, the cover picture of Science in June 1995. It was a big breakthrough in atomic physics, because this opened the way to a lot of very beautiful and potentially useful experiments. If you let the BEC escape from the trap, you get a coherent beam of matter waves, which is the equivalent of lasers, with the difference that the particles are not photons but atoms. And you have many, many experiments which have been done in this way. And these beams can interfere with each other. You can build gravimeters, you can build gyroscopes, which use these beam of atoms. You can also do the same kind of experiment with fermions, particles which have an odd number of fundamental particles in them. And for instance, if you work with lithium, which has an isotope, which is a fermion, and an isotope, which is a boson, you can compare the properties of boson and fermions. If you have bosons, they will all condensate in the ground state of the trap. If they are fermions, you can have only one atom per quantum state, which means that if you cool them, and this is the example comparing lithium-7 and lithium-6, if you cool a boson gas, it will become much smaller at a low temperatures than the fermion gas at the same temperature. And you can see in a kind of visceral way the difference between boson and fermions and the effect of the Pauli exclusion principle and on this system. So you have a direct, you can really make textbook experiments. You can also see the analogy with solid-state physics. If you cool bosons and fermions, they become superfluids at very low temperature. Boson, the reason is clear. Fermions is because they pair, like in the BCS, Bardeen-Cooper-Schrieffer superconducting theory. Pairs of fermions in very cold gases interact with each other and form loosely bound pairs which have bosonic properties. And you see that, for instance, if you put the system in rotation, you see that the ensemble does not rotate as a classical gas, it rotates as a quantum gas, which means that vortices are formed. And in a vortex, the velocity becomes larger and larger at the center of the vortex, whereas in a classical gas, the velocity, of course, increases with the radius. And if you try to put more angular momentum in the system, more vortices form, and the vortices interact with each other to form regular structures. And this can be done with bosons and with fermions. And this reminds us of the vortices arrays in superconductors of type 2. In the case of superconductivity, the vortices are magnetic field lines. And in the case of BEC or fermionic gases, these are lines of rotation. And the analogy is clear. If you write the Hamiltonian of the system, you find that for atoms and for superconducting electrons, the Hamiltonian has the same form, except that in the case of electrons, the magnetic field creates a Lorentz force. In the case of rotation, the rotation creates a Coriolis force, and the form of the Coriolis and the Lorentz form are the same, so you have the same physics. And this gives an interesting idea, the fact that you can simulate with these cold gases events which occur in solid-state physics, and you can make artificial magnetic fields, for instance, and you can study a lot of effects which are difficult to study in condensed matter physics because you control less well the parameters. And another field in which this becomes very, very fruitful is to build optical lattices with laser beams in 1, 2, or 3 directions, and to trap atoms at the nodes of these optical lattices, and you create artificial solids and study effects which would occur in the real materials at a completely different scale. And this is the domain of not quantum computing, but quantum simulation, which is developing very fast and very useful. A few words about detection sensitivity. This is again a picture of Kastler showing a sample which contained about 10 to the 10 atoms. And here you see the first picture showing a single atom. You see here a single barium atom in a trap. So you have a lot of scattering of light on the zillions of atoms that you have in the trap electrodes. And you see here the magnitude of the light scattering effect. A single atom can compete with maybe 10 to the 22 or 10 to the 33 atom because it is resonant, while the other one are not resonant. And this was first observed in the group of Peter Toshek in 1978, and then by Dave Wineland in United States, and again 10 orders of magnitude. So single atom physics have opened a lot of interesting things to study in quantum optics, for instance. If you have a single atom, and if it can emit a lot of photons when it scatters the light from a laser. But the difference with a classical source is that once it has emitted a photon, it takes some time for it to be re-excited. And so you have a kind of time lag between photon emission. It's called photon anti-bunching. And it's a quantum effect which has been studied in the 1980s. The other important effect is the quantum jumps of a single trapped ion. You see here the structure. You have 3 levels. The atoms is scattering a lot of photons on this transition. And this is a forbidden transition with a second laser, which sometimes brings the atom from the ground to this shelving state. When this happens, there is a sudden interruption of the scattering of light on the other transition, and you see this as jumps of the light. This is now used routinely in all ion trap experiments. In the 1980s, it was to some very surprising. There are many physicists who thought that quantum jumps did not exist. And the most famous was Schrödinger, who wrote a paper in the 1930s whose title was, "Are they quantum jumps?" with a question mark. In fact, he did not like at all this idea, but you see now that it has become common. And of course, if you do that with many atoms in a trap, you can study quantum entanglement and perform a lot of toy experiments for quantum information processing with ion strings. What is the connection with cavity QED? In fact, these cavity QED experiments and the ion trap are just the 2 sides of the same coin. In the case of ion trap, what you do is that you use electrodes to trap ions, and then you use laser beams to manipulate these ions. You use, first of all, the laser beam to cool the ions, and then by looking at the scattered light, you get information about the quantum state of the ions. In cavity QED, we do the opposite. We trap the light between mirrors, in fact, microwaves, and we send a beam of atoms across to extract information from the photons. Where is the laser here? Of course, the laser is used to prepare the atom. We don't use ground state atoms. We use Rydberg atoms, very excited atoms, which interact very strongly with microwaves. And in both cases, we use light-matter interaction at the most fundamental level. I want also to stress that it's called what we like to call in vivo physics, because we observe atoms without destroying them. This is maybe not so strange, but it's the stranger fact that you can also observe photons without destroying them. And this is new, because usually when you observe photons, you destroy them by the photoelectric effect, of course. But here the Rydberg atoms can be used to interact with atoms in a gentle way to extract information from the field without destroying the field. And this is what we have been doing in Paris. I don't have time to explain the details, but we can observe the quantum jump of light. You look at the photon field, you decide that you measure the number of photons by sending atoms across the cavity, and you find, for instance, 4 photons, and then after a while it goes to 3, to 2, to 1, and to 0, and the jumps are random. You cannot predict when they will occur. You can look at the statistics of these events, and you can see and observe and maybe use one day the quantum jumps of light. We can also prepare strange states of the radiation field. Again, I don't have time to discuss that, but these are pictures which are kind of radiography of the field in the cavity. And you see these 2 peaks correspond to 2 fields which have opposite phases. And in between, you have fringes in this picture which express the fact that this superposition has a quantum mechanical coherence. It's a quantum state superposition. And as time evolves, the fringes are washed out. This is the phenomenon of decoherence. And so this is a kind of illustration of this Schrödinger cat physics. You can prepare a system which is at the same time with one phase and the other, and suddenly it has to collapse into one or the other state. Of course, we see the two states because it's a statistical experiment. So this kind of experiment reminds us of the photon box experiments that Bohr and Einstein discussed at the Solvay conference in 1927. You see in this experiment, you have a box which contains photons, and you want to find out when the photons escape. And for that, you have a clock which triggers a shutter which opens or closes the box. I don't want to discuss in which context that they invented this, but in fact, we are doing something similar. We have a box, and the Rydberg atoms make the clock. In fact, we look at the phase, how the phase of the Rydberg superposition evolves, and this is equivalent to an atomic clock, and the measurement of this atomic clock gives us some information about the field in the cavity. So these are experiments that the founding fathers of quantum physics believe would never be done. They considered it was just a way to think about quantum physics, and Schrödinger said, as you may have heard, we never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do, and it always results in ridiculous consequences. So when I am asked why I am doing that, I say that half-jokingly that the main motivation is to prove Schrödinger wrong, that it's not the consequences are not ridiculous. What about the measurement of time? I would like to, again, to insist on the orders of magnitude. So I will recall a little bit of history. In the 14th century, the time was measured in churches by tower clocks. So it was a torque on a thread which was used, and the oscillation of this horizontal rod, and the number of oscillation was counted with a wheel which has teeth in it. Then, of course, there was an improvement with Galileo and Huygens in the 17th century. They replaced this very complicated system just by a pendulum, and the escape mechanism was counting the oscillation of the pendulum and transferring them into the motion of the hand of the pendulum. And then in the 18th century, there was an interesting development, which was to replace the pendulum by a spring, and this was a modern watch. And it was a chronometer, in fact, and it was developed with high precision by Harrison. The aim was to be able to keep the time for long times in order to have this, to be able to carry this watch on ships and to keep the time of Greenwich or London or whatever when you were at a different longitude to measure the longitude. And then the next improvement came only in the 20th century. It was a quartz clock, which was transferring the oscillation of a quartz cantilever, of a quartz rod, into an electric current using the piezoelectric effect. The principle is always the same. You have an oscillator which is coupled to an escape mechanism which counts periods and which also restores the energy, because otherwise the oscillator would be damped. Let's compare the precision. The tower clock has an uncertainty of 10⁻². It was about 1/4 of an hour per day. So you had to reset the time looking at the sun every day. The Galileo pendulum was a few seconds per day, the best one. You have to correct for contraction, for dilatation due to temperature and so on. But moreover, the pendulum cannot be carried on a ship, so it was not very good for that. The best chronometers were 1 second per month. And this was good for navigation because 1 month needs you a lot of time to go far. And the best piezoelectric clocks are 1 second per year. So you see that in 6 centuries, the progress has been 6 orders of magnitude, 1 order of magnitude per century. In the last 50 years, we have added 10 more orders of magnitude in 50 years. So you see, and this is because of lasers, essentially, not only lasers, but quantum physics and lasers. So you see how, starting in the 1960s, the accuracy of clock has increased first using the cesium microwave clock, and then optical clocks with a new slope. So the atomic clocks of 2015 are 10 orders of magnitude more precise than the best sports clocks of the 50s. They keep time with an accuracy of 10^13 seconds per day instead of 10^3. Of course, you know the principle of the first atomic clocks were microwave clocks. Again, the heritage of Rabi. And Norman Ramsey was a student of Rabi and the mentor of Dave Wineland. So you see that one advice to get a Nobel Prize is to be in a long lineage of scientists. You see, the principle of the clock is just, it's an atomic beam, a molecular beam, and the trick is to have now the field applied in 2 pulses instead of 1, and then you have an interference effect, and instead of having just a Lorentzian line, you have fringes when you sweep the frequency of the microwave, and if you can lock the microwave to the central fringe, you have a very stable source of microwave. And in the microwave domain, there are electronic means to count the frequency, so you have a clock. And this clock immediately gave an uncertainty of 10^14 instead of 10^8, so 6 orders of magnitude in one step, 1 nanosecond per day. And 1 nanosecond per day is very important because it means that if you reset the clocks every day, you have now a clock which can give a signal which will have an uncertainty of only 30 centimeters per day, and this is why the GPS system is so precise. But of course, for the GPS system, you have to correct for all relativistic effects. So I take the GPS as a fantastic example of an application innovation which uses fundamental quantum physics and fundamental relativity, special and general relativity effects. Everybody uses that every day in daily life without any astonishment. And everybody talks about social needs, the fact that you have to develop research because you have to help solve problems. In fact, you solve the problems without thinking about them. Einstein and Bohr and Schrödinger never thought about the GPS, and this came after a long time of basic research. So what about the lasers? The lasers improved the atomic clock by 2 orders of magnitude just because you can use colder atoms which stay a longer time between the 2 pulses. And what you do is that you make an atomic fountain. You see here the fountain, you prepare a cold gas of atoms with these beams, and then you push the atoms up, and on the way up and down, they interact with the microwave twice. And you detect them when they come down in this laser beam by looking at the fluorescence of the atoms, which is different depending upon whether they are in the upper or in the lower state of the transition. And then you get very narrow fringes because the separation of the period of the fringes is inversely proportional to the separation time. And now you can count time with an uncertainty of 10^16. But this is not the ultimate. You can even do much better if instead of counting microwave, you count optical frequencies. And the problem was, how do you go down from optical frequencies to microwave and then to an electronic counter? And for that, the breakthrough was, of course, the frequency comb developed by Ted Hench and John Hall. The idea is to have a multi-mode laser with a lot of modes and to lock them in phase together. And when you do that, the phase-locked lasers give a train of pulses. You have an interference effect which beats up the light at a very short time, and then the light goes down and goes up. You have here a picture in the frequency in the frequency domain where you see how the interference builds up this train of pulses. In the time domain, what you can think of it as a kind of bullet of light going back and forth between the mirror and escaping from one of the mirrors, and gives a train of very short pulses. Each pulse has only a few oscillations of the light beam in it, but if you add up all these pulses and look at the Fourier transform, you find that it's a comb of very well-spaced lines in the spectrum, and you can cover an octave of light in this way. And the most important point is that you can lock the repetition rate to an atomic clock, and then you have a kind of ruler which gives you any frequency with the precision of the microwave clock. So the principle, for instance, this is taken from Ted Hench slide. You have a laser, you divide it in 2 parts. One part is sent to look at a line, for example, in hydrogen, and you lock this laser to the hydrogen line, and then the other beam is compared to a frequency comb, which is itself locked to the cesium clock. So then you can make absolute measurement of atomic frequencies with a precision of 10^13, 10^14. But you can reverse the system. You can get rid of the cesium clock and use now the atomic line itself, the atomic system itself, as a way to lock the frequency comb. And now you have an atomic clock which is based on an optical frequency. And there are two kinds of clocks which are competing to become the new time standard. One which is based on a single aluminum or magnesium ion. This is experiments which come directly from Dave Winans' group. Or you can have a bunch of atoms in an optical lattice and lock a transition of these atoms, neutral atoms, to a frequency comb. The precision is now of the order of 10^17 to 10^18, which is 1 second in the age of the universe. It means that if two clocks had started like that 14 billion years ago, they would not drift with respect to each other by more than 1 second. This also means that you can make general relativity experiments. If you take two clocks, and if you bring one up by a few centimeters, the ticking rate of the two clocks will become measurable. In fact, this has been done with 33 centimeters. Maybe because it was done in America, it was 1 foot. So 1 foot is enough to see the difference. And this kind of clock could be used to see small mass inhomogeneities inside the Earth, or to make some kind of prevention, warning before earthquakes, because when there's small motion of masses inside it, the clock time will be different. Now I see that I have no more time, but I will conclude with the last topic I wanted to discuss, which is the high power lasers and ultra-short light pulses. And my excuse to go fast is that Ferenc Krauss will describe this afternoon, and also I don't dare to talk in front of such specialists here and people working in this field. I just want to stress the fact that the evolution in the peak power of laser has been strongly correlated to the shortening of the pulses, just because in order to get short pulses, you need strong nonlinear effects which require power. And you see that there have been two periods. The first period, which is due to essentially to mode locking, the effect I discussed, which increased the power tremendously. And then there was a plateau due to the fact that one reached the level at which you are destroying the amplifying medium which was used to get more power, so it was not possible to go to larger power. And this increase here was correlated to a decrease of the pulse length to a few femtoseconds. Then the same plateau occurred, and this happened because a technique called chirp pulse amplification was invented by Gérard Mourou and others about at the end of the 1980s, and a big increase occurred, and this is correlated to the decrease of the pulse length. And the next slide gives the principle of chirp pulse amplification. The amplifier here is a critical element. So if you have a short pulse to start with, you start by stretching the pulse, making the red wavelength going a shorter path than the blue one, and the stretched pulse can be amplified without damaging the medium. And after that, you compress the pulse again, and you get a huge pulse in which you have a lot of power. And this is the kind of pulse which are used for attosecond physics. So I defer to Ferenc Krauss. I just remind the principle that you just focus this huge power of a very short infrared pulse on a gas jet of a noble gas, for instance. And the principle which has been developed by, explained by Paul Corkum back in the 1990s, is that what happens is that the first time the pulse reaches a maximum value here, electrons are ejected from the atom by instantaneous field ionization, and this electron which goes away comes back on the atom when the light field reverses itself, and when it collides back with the atom, at this time there is a nonlinear process which produces a very high harmonic of the field and a very short pulse. And the important point is that you have now two pulses, the original infrared pulse and the very short pulse, and you can delay one with respect to the other. I do a lot of stroboscopic tricks that I don't have time to discuss, and one of the most of the most spectacular result is this, the fact that you can now take direct pictures of an optical field which oscillate at 10 to the 15, and you can use all this kind of physics as powerful probes to study ultra-fast electronic processes, and Ferenc will talk about that. So I think it's time to conclude. I want to come back to what I thought was a very important point, that AMO physics, which I must tell you in the 1960s was considered as a boring field. When I got into this field, a lot of my friends told me, but why are you going in atomic physics? You will take spectrum all your life. It's boring. You should go in particle physics. And I am glad that I stuck to AMO physics. It made connections with condensed matter. For example, artificial atoms are using all the technique of atomic physics to do wonderful things. Cold atom simulate solid-state system, as I said. There is a connection with astrophysics. A cold fermionic gas, degenerate fermionic gas, simulates a situation of neutron stars, which are made of fermions. You have a connection with particle physics. You can study whether interactions symmetry are violated in atomic physics. You can also, by comparing atomic clocks, see whether fundamental constants are varying with time, which has a connection with particle physics and cosmology. Attosecond physics makes the bridge with chemistry and biology. And of course, so you have a connection with quantum information science. Last word in conclusion, I want to stress the permanent dialogue between blue sky research and innovation. All of this story started with the observation of nature. I remind you that quantum physics started with the observation of strange properties of light, like the photoelectric effect, which could not be explained classically. So this leads to theoretical models, like quantum theory, which predicts new effects, atom-photon interaction leading to the laser. So it leads to novel technologies which allow you to develop new devices, laser interferometers, atomic clocks, and this gives you tools to perform more precise observation which confirm or falsify the theory. So this, I just want to finish by acknowledging my co-workers. I have been working with Jean-Michel Raymond and Michel Beaune for many, many years, and this is a picture of our group on the top of Collège de France. So you see that we are working in a nice environment with a lot of culture beyond physics. In fact, there is a tower here, which is a tower in which Pascal in the 17th century demonstrated for the first time the effect of the atmospheric pressure, the fact that atmospheric pressure decreases when you go higher in altitude. This is Tour Saint-Jacques. And I also want to say that I have had a long list of students and postdoc and co-workers over the last 40 years. And what I am most grateful and proud about is that about one half are foreign. They come from 20 countries, and this illustrates the international nature of science. And I will stop here and apologize for the delay. Thank you.